Previously, we discovered a certain fact. We found out that if an infinite series converges, then the limit of its individual terms must tend to zero. This naturally makes you wonder if the reverse is true. If the individual numbers a(n) tend to zero, is that necessarily a sign that the infinite series based on those numbers converges? Unfortunately, the answer is no, as we'll see in the following example. I'm going to look at the infinite series 1 over 1 plus 1 over 2 plus 1 over 3 and so on. That is to say, the sum I equal 1 to infinity 1 over I. This is known as the harmonic series, and it's the easiest example of some bad behavior that we're about to see. I want to imagine adding up a chunk of this series, starting at some particular number 1 divided by k, and continuing until I've doubled the index on the bottom. If I count how many terms I have, this would be 1, 2, out to k, and then that one would make k plus 1 terms altogether. Since the top of the fraction is constant and the bottom of the fraction gets larger as we go from left to right, the smallest one of these terms is the last one, 1 over k plus k, of course, 1 over 2k. So I'm adding up k plus 1 things, each one of which is at least 1 divided by 2 times k. The sum must be at least as big as k plus 1 times 1 over 2k. This number is larger than k times 1 over 2k. K times 1 over 2k is 1/2, though. It may not be obvious, but this ruins any chance that the infinite series that we're looking at can converge, as we will see. Let's look at this fact. 1 over k plus 1 over k plus 1 out to 1 over 2k is at least 1/2. S2 is 1 over 1 plus 1 over 2, which is obviously bigger than 1/2. The next term in the harmonic series would be 1 over 3. If I add in 1 over 3 and then continue adding terms until I reach 1 over 6, which is 2 times 3, then I'll have another 1/2 as an estimate. 1 over 1 plus 1 over 2, and then 1 over 3, 1 over 4, 1 over 5, and 1 over 6. This is a partial sum of my series. This is partial sum number 6. The sum of the first two terms is at least 1/2, and because of the double the index business, 1/3 out to 1/6 is also at least 1/2. So S number 6 is at least 1/2 plus 1/2. S number 6 is at least 1. The next term in the harmonic series would be 1 over 7. If I double 7, I'll get 14. If I take what I had before and then add 1/7 through 1 over 14, what I'm adding in is at least 1/2 more than what I had previously. S number 14 is at least 3/2. The next term would be 1 over 15. Double 15 to get 30. S number 30 is going to be at least 2, and there is no end to how many times I can do this. I can make the partial sums as large as I want to make them. This is really the right way that we should express this. People often say that because the fact that the partial sums become indefinitely big, that the sum I equal 1 to infinity, 1 over I equals infinity. But this is a very bad way to express it because it makes you think that there's a number named infinity to which this infinite series converges, and there is no such thing going on here. 100 things or 1 million things, any finite number of AI and BI numbers will behave in this manner. In the case of an infinite series, where we have an infinite number of terms, the situation is a little bit more delicate. The value of an infinite series is a limit. It's a limit of the partial sums of the series. Now, within this sum, k is a constant. Later, we look at all the cases where the k becomes indefinitely big, but for just this part, k is not varying. So for the sum I equal 1 to k, ai minus bi, there can't be any objection to splitting this up into the difference of two separate sums. The problem comes when I want to split this up into the two different infinite series, and we have to remind ourselves, when is it legal to do the following? When is it legal to write the limit of a difference of two things as the limit of the first one minus the limit of the second one? The answer is when both of those limits exist. If even one of them doesn't converge, then it's not legal to write this. The relevance of this is that if I want to look at the sum I equal 1 to infinity, 1 over I minus 1 over I plus 4, because of our experiences with ordinary sums, the first thing that I think of doing is to split this into two sums and deal with them separately. To emphasize the fact that this isn't a good idea, I'm going to write it out using the red pen of wrongness here. Everything you see in red is wrong. So that is wrong. The infinite series that we're interested in is a limit. Both of these separate infinite series are limits. It's all right to split the limit of a difference up into the difference of the limits only when both of the limits involved converge. In this case, both of the infinite series. But we already know that that, being the harmonic series, does not converge. That is 1 over 5 plus 1 over 6 plus 1 over 7, and so on. Except for the first few terms, it's the harmonic series. That doesn't converge either. So by writing this, I've written nonsense. This statement is not true. Now, if I didn't know any better, I would say in the preceding pages, we sometimes write things like this equals plus infinity, and that equals plus infinity. If I didn't know any better, I might be tempted to write this. That doesn't make sense, but even if I believed that it did, what am I supposed to write down for infinity minus infinity? In any case, the red calculation is completely wrong, and what I want to do is to look at this the right way. An infinite series is the limit of partial sums. So we're going to look at a partial sum and then take its limit as the index tends to infinity and see what we get. Thinking only of this part first, and then later thinking of taking the limit as k tends to infinity, k is a finite number. This is an ordinary sum. I don't feel bad at all about splitting it up into separate sums. What we'll do is we'll simplify the expression inside the square brackets and then take the limit as k tends to infinity. The key point to observe is there's going to be some overlap between the terms of the first sum and the terms of the second one. In the first sum, the first term is 1 over 1, and then 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. The last term in the first sum is 1 over k. In the second sum, the first term is 1 over 5, and then you will have 1 over 6, 1 over 7, and so on. The last term in the second sum is 1 divided by k plus 4. When I write out on the next line these sums, I'm going to be sure that I write out enough terms so that I can see what terms are in common between those two sums. In the first sum, I'll write out 1 over 1 out to 1 over 5, and then the rest of the terms of the first sum continue until I get to 1 over k. In the second sum, the last term is 1 over k plus 4. The one before that is 1 over k plus 3, 1 over k plus 2, 1 over k plus 1, and 1 over k. Looking at it this way, I can clearly see that all terms 1 over 5 out to 1 over k are going to cancel out when I do this subtraction. If I take advantage of that fact, I can write the following thing down. I need to emphasize that these trailing terms that involve k, there are only a finite number of them. If there were an unending stream of these things, the resulting part of the sum would diverge on me, as we've seen before. 1 over 1, 1 over 2, 1 over 3, 1 over 4 do not depend on k. As k tends to infinity, that term goes to 0. So does that one, and that one. The limit of the partial sums exists and is 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. The value of this infinite series ends up being 25 divided by 12. This type of series where many terms cancel out are called telescoping series, and it serves as a good example of how careful you have to be when you're manipulating infinite series, you can't just treat them like they're ordinary algebra sums because you end up with infinity minus infinity, where you should have ended up with 25 over 12. I hope that this is clear enough for everybody to understand and that you're having a good day. I'll talk to you again soon.